Okay, I think this is time to start our Matlantis webinar. It is just 4 o'clock in Japan and 9 o'clock in Europe. So thank you everyone who for those who registered and who are with us today. So my name is Rudy Coquet. I'm working for PFCC, the company promoting Matlantis, and I will be your host today. So let's see, we have already quite a few participants. As attendees, you cannot see how many people actually are joining this meeting, but we already have a few. That's very good to see. So let's start. All right, so this is the agenda for today. We have just a few minutes for welcome, a few welcome words. Then we will have an introduction to Matlantis by PFCC. This will take about 10 minutes. And then we will continue with the main part of the webinar, which is the case presentation by Mr. Lieven Bekaert. And this will last 30 minutes. And after this, we will have a Q&A session of 15 minutes. Regarding the Q&A session, you will see in Zoom, you have an option, an icon, which is called Q&A. If you have questions, just click this and you can file your question. It will be seen by the panelists, by the host of the meeting. And we will take your questions and come back to them at the end of the webinar. So do not hesitate, do not wait for the end to ask something. Just type your questions in and we will treat them, we will answer them at the end of the webinar. I think this is what I wanted to mention about the practical things regarding the organization. So as I said, this is being organized by PFCC, so the Japanese company, Preferred Computational Chemistry, and in partnership as well with the Association of Materials Valley. And we have here as a co-panelist, my ex-colleague and friend, Andreas Brumby. So yes, Andreas, I wanted to thank you for your help promoting this event. And yeah, this is a pleasure to see you again and to have you as part of this webinar.
Yeah, thank you very much, Rudy, for contacting me. And I think it's really great that we have this cross-continent webinar. Learning cross-continents, I think that's really something we have to do. And you all know that Japan with Toyota, they were the first with a hybrid car. So they were the first who put a small battery in the car. And therefore, it's very good now to hear what the research in Japan is further doing. I see some familiar name in the participant list, so I'm very happy. And it's good that we make a recording. So I'm looking forward to learn what Matlantis is doing, what AI can do, and neural networks. Thank you very much.
Thank you, Andreas. All right. Now, let's continue with the introduction to Matlantis. This will be about 10 minutes. And as I said, I just repeat again, if you have questions, please type your questions in the Q&A. And we will take those questions and answer them at the end of the webinar. Okay. So first of all, this is our very first slide. There's the at the top of the slide, you'll be find here the website to our product. So please, if you have not done so, do not hesitate to visit and to have a look. First few words about PFCC. So that we could PFCC is actually our company, Preferred Computational Chemistry. I think most of you have not heard about of this company before. So we have just a couple of slides to explain who we are. PFCC actually is a joint venture between 2 other Japanese companies. The first one being Preferred Networks, which is a Japanese AI tech leader. It can be defined as a unicorn. And the second company, mother company, is ENEOS. So ENEOS is a oil company. It's the largest oil company, not to be mistaken with ENEOS in Europe, which is a chemical company. And it was established in 2021. So we are now celebrating our second birthday. The goal was to accelerate materials discovery for a sustainable future by using computational chemistry instead of experiments. And to do this, we are providing Matlantis, which is a high-speed universal atomistic simulator. The status for the company today, I think this is also interesting for those who don't know yet this company. We are doing very well in Japan, so the domestic market is going very strong for us. We have already more than 50 organizations and more than 350 licensed users for the Matlantis, and we serve a whole range of industries. So of course, academia included, but it's not limited to chemicals and catalysis, but also other things, other applications such as the rubber industry, semiconductor industry. And you see here on the right side a few names of for the companies who actually are using our product today. Not all of them are listed, but you have a few. And since we are good, doing pretty well in Japan, we are now trying to do the same outside Japan. So this is our next challenge. And now we are trying to go to global market. We have been testing the software, the service already in the US, in the EU or South Korea, to name a few. We officially launched our service in May in the US, and the next target is to do the same for the European market. So this is a business status for the company. Now, let's say maybe not most important, but most interesting for most of you is actually Matlantis itself, so the atomistic simulator. The goal here is not to give you a detailed view, but just an overview of the service. There will be links to the research papers in the presentation. And before I start, I have also to mention that we are recording this, and we will make the recording available to you and to those who registered, even though they could not join today the meeting, the webinar. So what is Matlantis? So first of all, what is the mechanism behind Matlantis? So Matlantis basically is built on a lot of training data. And when we say a lot, that's quite a lot. That's more than 30 million of DFT simulations for various molecular and crystal structures, including disordered materials, and also materials that are not supposed to naturally exist, actually, to train Matlantis to have let's say, a better training. We are relying on a graph neural network that was designed by Preferred Networks. We call this PFP, so Preferred Potential. And this is connected, of course, to machine learning. And with machine learning, we managed to achieve accuracy, which is very good compared to DFT. You can actually plot the energy calculated by Matlantis against the energy calculated by DFT, and you find a very good correlation here. Very important as well, the model is ready to use, so there is no need to prepare training data or machine learning tools. So this is almost like ab initio. You just design your model, you load your atomistic coordinates, you tell Matlantis what to do, and it will calculate it. The main features are speed and universality. So speed, first of all, because if you compare to DFT, we have done, of course, several comparisons, but you can actually take a very simple platinum qubit phase-centered cell of 256 atoms. DFT will take you about 2 hours with the conditions that we have listed here at the bottom of the screen, and Matlantis would take a fraction of a second. More interesting is if you go up to 3,000 atoms, which becomes almost impossible for DFT, even using supercomputers, or it's very, let's say, time-consuming. Matlantis will only take a fraction of a second again to do a single point energy calculation. Universality is the second very important feature, because you can apply Matlantis to 72 elements, and this is something that we are improving. So you see, it can actually treat the most important elements for most of our customers, including transition metals and those that are needed today for topics such as catalysis or semiconductor. A speed advantage. So I was showing you before a comparison with DFT. Here, this is a comparison with actually a real-world comparison for one of our customers, comparing VASP on a supercomputer, and both on a local supercomputer and national supercomputer, and doing the same thing with Matlantis. You see Matlantis in every case is at least 30 times faster than DFT, even though it's running on a supercomputer. So the speed is really interesting. Now the capabilities, the basic features. I will not spend too much time on this. As I said, we will share the presentation with you, so you'll be able to read through the physical properties that can be calculated. But you basically calculate or compute the energy and force from your atomic structure, and you do that with the same accuracy as DFT. And I hope that the case study we will present today will be a proof of that. It's versatile. As we said, you can actually apply this to a lot of different elements. It's scalable and secure. There is no need to install any hardware or software. We provide this as a cloud service. So we are relying today on the Amazon cloud service. So this is a global standard, and you access this from a web browser. It's flexible and customizable because you can actually write your own scripts. Matlantis is running on Jupyter Lab, so it's a Python environment, and you can use either ASC, so the atomic simulation environment, and define Matlantis as a calculator, or you can use LAMPS. So the two are possible. So if you are familiar with ASC, that will be very easy for you to actually use Matlantis. It includes very simple graphical interface, but of course you can use your own graphical interface, or the one that you like to use to design your model and to display the results or the outputs. Now, what is the system environment looking like? So this is what we have. This is an example for one customer, so one company that we will call here ABC. Each user will have access to its own Jupyter notebook. So you see the data and what each user is doing is independent from the other users. Of course, all this stays within the environment of the company. It's completely sealed from other customers and even from PFCC. We do not have access to your data. They are automatic backers, but we cannot see your data. And then the calculations actually will run on what we call an inference system. So this is when it will go to GPUs. So when I was mentioning the Amazon Cloud Service, this is where the GPUs will be located. And the Matlantis will be running on those GPUs here. There is also a group drive, which is independent for each company, of course, and where you can actually share files between yourself and your colleagues to make it easier to work together. So our services, as I said, we provide Matlantis. So this is our universal neural network potential that we just described before, which is also linear scaling. Our cloud service that I just presented, Jupyter Lab environments, which is of course very flexible, very powerful. Documentation and sample. I have to mention here that we also have interactive tutorials. By interactive, I mean that you have the real Python scripts that you can actually change and run yourself. So it's a way to learn by doing. And of course, last but not least, very important for us is the customer support we provide. This is done mostly by mail or on the web form. We are expanding, as I said at the beginning, to other regions outside Japan, and we are now also considering to have in the near future a physical presence as well in the US and in Europe at least. So now, if you are interested in trying Matlantis, of course, we provide our service to, as I said, academics, also, of course, to private companies with different pricing that we can discuss with you. But there is also a free trial that can be started. This will run on a system that is exclusive to you. And so there is the files, of course, will not be shared with anyone else. And the system will be non-limited, which means that it will run as a Matlantis calculation, the same way as if you pay for the service. So you have a real chance to actually test and to compare to what you are doing today with other codes or other methodologies. It's available in already countries such as the North America, EU, and UK. So that will cover, I guess, most of you today joining this call. We have also South Korea, Taiwan, India, Singapore, and Saudi Arabia. So the best way that what you can do actually is to contact us by visiting our website. Just send us a message. There is a very easy to find contact button, and we will come back to you with more explanations on Matlantis itself and how this can fit what you do at work and how to start the free trial. So this is a summary. So Matlantis can, I hope I managed to show that it can dramatically accelerate elucidation of mechanisms at the atomic level. It should enable you to do a large-scale screening for fast materials discovery. Because it is so fast, you can actually screen a lot of different possibilities. And because of the speed also, it will facilitate the digitization of your R&D department. And I invite you to have a look at this research paper. It's a network communication where you will have much more explanations on the background and where Matlantis is coming from a scientific point of view. And with this, I will finish my presentation, and I will give now the words to Lieven, who will have 30 minutes to show what he has been doing with Matlantis as part of his PhD work that he is actually just finishing. And I think I will let him introduce himself. He will do a better job than what I can do. So, Lieven, if you would like to start, the floor is yours.
Okay, thank you very much, Rudy, and also thank you to Andreas and to everyone watching today. Let me first share my screen. Can you hear me?
Yeah, we can hear you.
Okay, perfect. Thank you. And can you see my screen now?
Yes, we can.
Okay, perfect. Okay, so thank you everyone for joining. I'll begin with the presentation. So in this presentation, I will talk about how we use Matlantis. Matlantis uses AI in its neural network potential to search for innovative battery materials. And in our case, I'll give you 3 examples. The first 2 examples are of my PhD research, which focused on the negative electrode and solid-state electrolyte interface in sodium metal batteries. And this 3rd example is a short-term research project that we did together with ENEOS on investigating degradation pathways of lubricant additives using Matlantis. And what I really want to show you is how versatile Matlantis is. So in the first 2 examples, we focus on crystalline and ionic compounds, whereas in the 3rd example, we focus on molecular systems, so organic compounds. So very different properties of materials. And we were able to simulate both using Matlantis. So first, a short introduction. My name is Lieven Bekaert. I'm a final year PhD student at the Free University of Brussels. And I'm also doing research now at the Nagoya Institute of Technology in Japan. And in my research, I've been using both ab initio, so the conventional techniques, as well as Matlantis. So I have experience with both, and I really can give you a good idea on the differences and the benefits of using Matlantis. So let's begin with the first case study. This research was published in the Journal of Physical Chemistry C this year. So it's titled Investigating Decomposition Reactions at Battery Solid-State Electrolyte and Electrode Interfaces Using Matlantis. Now, the research that we focus on is on sodium metal batteries. Now, you'll probably heard of lithium ion or lithium metal batteries, maybe not so much about sodium metal batteries. And there's a good reason why you hear about lithium. If you look at the properties of lithium, it is much smaller, it's lightweight, and it has a very negative standard hydrogen reduction potential, meaning that you can store much more energy per individual atom. However, sodium also has several advantages. For example, it's much more geologically abundant and has a lower price. And especially towards the future, we're seeing that the price of lithium is increasing recently. And with the use of more electric vehicles, this is expected to increase towards the future. So what we really want to do is we want to work towards a future in which we can use lithium-based batteries for the applications where you need compact and lightweight batteries, for example, in mobile devices and airplanes and cars, for example, and that you can use sodium, even though it's heavier and slightly larger, for applications where you want to store, for example, renewable energy. And we call that stationary storage. And so our research focuses on sodium batteries because we also have some new challenges using that material. Now, which part of the battery do we study? Well, batteries, in the case of lithium, rechargeable lithium and rechargeable sodium batteries, consists of 3 parts. So you have both electrodes, a positive and a negative electrode, and in between you have the electrolyte. And what happens is that when you're using the battery, electrons will move through an external circuit, and at the same time, you have the ions which move from one electrode to the other. And in order to have a battery working properly, you want to have the interfaces between both electrodes and the electrolyte running smoothly. And I don't know if you can hear, but actually it started thundering a lot in Nagoya, but please ignore that. So the interfaces, they must remain stable over time. And when we go to sodium metal batteries, because sodium cannot store as much energy as lithium per atom, it's also larger and heavier, it's most interesting to use only pure sodium as the electrode. Now, for example, in lithium batteries, now we would use graphite to store the lithium ions. But in the case of sodium batteries, it's much more interesting to use sodium metal. Now, this has a high energy density, but it has a big problem in that it is extremely reactive. And so for that reason, we need to focus on studying the interface with the sodium metal electrode and looking at how we can ensure that there's a long-term stability of the battery. Now, in our case, we also looked at this electrolyte material, which is the Na3PS4 solid state electrolyte. So it's solid state, meaning that it is not as flammable and it doesn't have as many hazards as liquid electrolytes, which are conventionally used in batteries nowadays. And it also only contains sodium and no other transition metals. So you have a low cost and high sustainability aspects related to this material. And so our research focuses on the interface between the sodium metal electrode and this Na3PS4 solid state electrolyte. Now let's go immediately to modeling interfaces. And we know that there are limitations in computational methods. You probably know that we have limitations in the computational power that we can use, the computational resources that we can access. So we always have to make a trade-off between the accuracy that we can achieve and the size of the system, how many atoms, and also the simulation length. So how long you can run the simulation if you're doing molecular dynamics. And the way that we can leverage both of these is by using approximations. Now, here are some examples of techniques that we can use, and this is mainly focused on molecular dynamics in this case. So classical molecular dynamics is a technique in which we don't use an explicit electron description. And most of you will already know that in classical molecular dynamics, we consider atoms somewhat like solid spheres. We don't really make a big distinction between the nucleus and the electrons surrounding it. So we don't use the Schrödinger equation exactly to solve how the electrons behave. And as a result, because of these approximations, it is not so computationally expensive. And as a result, we're able to achieve very long and large size and time scales. But one of the problems is that because of these approximations, we need many parameters. And that's why we need this force field. But in the case of interfaces, when you have two very different types of materials coming together, having an appropriate force field containing those parameters is not very easy. And so for that reason, it's very difficult with classical MD to study interfaces. Another example, another effect of not using an explicit electron description is that you're not able to simulate reactions, and depending on the size of the system, you need to have access to a supercomputer. Now you can overcome some of these problems by starting from scratch, by using ab initio techniques. And for example, AIMD does include an explicit electron description, but as a result, you'll know that density functional theory and related methods have a very high computational expense. And as a result, you are very limited in the size of the system and the time scale that you can reach. But the advantage is that you don't have to have many parameters, so you don't have this force field requirement, and you are able to simulate reactions at ease because you do have that electron description. Now, because of the computational expense, you do need to have access to a supercomputer. And back in 2022, I published the first paper for my PhD, only using ab initio MD, so that was before I started using Matlantis. And I will give you some examples of the benefits of using Matlantis as opposed to having the experience in only using ab initio techniques. And then we come to Matlantis. So in the last few years, we've seen not only in chemistry, but in many different domains, a real evolution in the use and the development of machine learning. And that's how neural network potential molecular dynamics came into play. So in essence, we're always recalculating when we're doing ab initio techniques. We're recalculating the energy and so on, and the wave function from scratch for many systems. But in reality, we can see similarities between those systems. So it would be much more interesting if you can save all of those similarities into a model and not have to redo those calculations. And that is what these neural network potentials are. So we do have an explicit electron description because we learn from ab initio techniques, and because we just have to enter the requested data into the model, we can get it very quickly. So the computational expense is much lower. And as a result, you're able to achieve longer size and time scales than ab initio MD. Here too, you have same properties as ab initio MD, so you have no force field requirements. You are able to simulate reactions, and there is no need to access supercomputers, of course, depending on the size of the system. But if you keep to the size of the systems that we are going to show you in this presentation, then it suffices to have no access to a supercomputer. And Matlantis also solves that problem by providing the online calculation environment. So let me give you two examples of these, the advantages of using Matlantis compared to our previous ab initio methods. So this is an example of one of the simulations that we use in the paper. We have sodium metal on the right side. We have the solid state electrolyte on the left side. So we have sulfur is yellow, sodium is the larger dots, and we have phosphorus, which is purple, which contains around 170 atoms. And we ran it on 4 nodes on the Belgian supercomputer, with each node 28 processors per node, so that's 112 processors. We have optimized the parallelization parameters, so that's with kpar and ncore, for example. For a time step of 1 femtosecond, it took 72 hours, that's a wall time, to only get a simulation of 14,000 femtoseconds, so 14 picoseconds. That's an extremely short time, especially for also a very small system, when in reality, you really want to study much larger systems when you're looking at battery materials. And therefore, if we put this into contrast with looking at how Matlantis performs, so here is a simulation file of around 1,100 atoms. Remember, Matlantis is able to simulate much larger systems, but in our paper, we had to study many different situations, many different conditions. So for that reason, we limited ourselves to 1,100 atoms, using only 1 GPU as part of the online calculation environment with an identical time step, and using Matlantis. In less than a day, we were able to achieve 200,000 femtoseconds. So that's 200 picoseconds. That's a significant increase over the results with ab initio MD. And as a result, we were able to get many more results in a shorter time. And we were able to publish 2 papers this year using Matlantis. Now, of course, when you're using a neural network model, it's important, and there's a risk, of course, that with any machine learning, that you can blindly trust the results, and in the end, you get this black box model, which you blindly trust, but in reality, it might give wrong results if you extrapolate beyond the known data, for example. And so that's why it's always important, and this is valid for Matlantis, but it's also valid with other techniques, to always perform a validation to make sure that the data is working, that the calculations are working properly. And so in this case, we performed a downscaled size of the simulation because you cannot simulate thousands of atoms that easily in ab initio MD. And we plotted it versus the neural network potential MD from Matlantis, so the energy results. And as you can see, it performs really well. There's a slight deviation at higher energy, but that has to do with the input structure. And the mean square error is 3.12 milli-electron volts, which is a really reasonable number, especially when you compare it to other machine learning potentials nowadays too. So let's then show you some of the results that we were able to achieve using Matlantis. So here is an example of our input structures for the simulation. So we have a vacuum layer on both sides. This is to focus the reaction in between so that no atoms will hop outside and come on this side and start to react. And on the right side, we have sodium metal. On the left side, we have the Na3PS4 solid state electrolyte. And so when we make the structure, we can upload this file. Many different formats are accepted because they use the atomic simulation environment, so the ASE software. So you can get many software formats to be read by those scripts. We upload it to the online working environment. We then run the calculations, and you can then choose to either post-process the results online because it's fully scriptable using Python and notebooks, or you can download and perform analysis with your own software. Now, the system that we've been analyzing, especially in this first example, it's an ionic system. So you don't really have that many covalent bonds except for the phosphorus-sulfur bonds. So what happens when you look at the output structure, you see this very mixed structure. It's very difficult to see what is actually happening. And here too, as I'll show you, Matlantis provides very unique tools to analyze this, as I will show you in the following slides. Now, in our research, we decided to use a total trajectory analysis approach to study this system, which means that we not only look at the input structure and the output structure, but we also look at what happens in between. So there's several steps that we've taken to do that. And I will just give you some examples of our process. So the first thing that we can do is to perform a visual analysis. As you can see in the beginning, we have a very distinction between the electrode and the solid state electrolyte. And over time, you get this interface. It starts to move upwards as sodium starts to mix into this solid state electrolyte and also starts to react. But it's very difficult to actually see what happens. So if we zoom in a bit, then we can see that what actually happens is that these PS4 groups, which are present in the solid state electrolyte, they break down upon reaction with sodium. So sodium gets in between those phosphorus-sulfur bonds and then breaks off sulfides, and you get PS3, PS2, PS, phosphide, and sulfide groups. But of course, visually, there's a lot of information, but atoms also have electrons, and so atoms have a property called charge. It's really interesting to be able to, analyze the charge and how it changes during these simulations. And here, Matlantis really provides a very important way of doing this, because what you would conventionally do is you would use, for example, Bader charge analysis. So Bader charge analysis, if you run it on a small system, it already produces many large output files, so you're limited with your resources. And especially with more than 1,000 atoms, that is very difficult to achieve. But with Matlantis, we can obtain this in just a few seconds, so it's really fast. So I'll just give you an example. So this is the situation at the beginning of the simulation. This is at 400 Kelvin. So we have separate plots for sodium atoms, phosphorus atoms, and sulfur atoms. And on the vertical axis, we show the distance, so the z-axis. So we have on top sodium metal with charge 0, and we have below sodium ions with charge +1. We have phosphorus atoms in the PS4 groups, and we have PS4 groups, also some minor sulfide and sulfur, but that is to do with the way that we have to make this input file. There will always be these borders which expose only sulfur atoms. And what happens at the end of the simulation is you can see that most of the sodium has reacted. All of the sodium metal has produced sodium +1, so sodium ions. We also very nicely see how these PS4 groups have decomposed into PS3, PS2, PS, and eventually phosphide groups. And you can also see how many of each are available. So it also shows which, for example, groups are more unstable than others. And the sulfides have also formed, and you can also see exactly where those sulfides have formed. So once again, with Matlantis, you're able to get this data in less than a second for all of the atoms in just one simulation frame. So this is a very significant improvement over conventional ab initio techniques. But as I mentioned, it's not only the input structure and the output structure, which contains very, very valuable information. It's also what happens in between these two. And so that's, once again, something which Matlantis is really good at. It can calculate the atomic charges overall simulation frame. So it's, for example, for our simulations, it was 200,000 frames, 200,000 femtoseconds. And we're able to get those results in about a minute. So it really shows how powerful Matlantis is. And when we do this, then we see this. So because we have many atoms, we have more than 1,000 atoms. So what I did is I calculated the average of the atomic charge separately for the different elements. This is the solid line. And then in the standard deviation, which I calculated, is the shaded area here. And you can see that over time, for example, sodium, it begins with sodium metal, charge 0, and sodium ions, charge 1. And so what happens is over time, sodium metal reacts. So the standard deviation decreases as now only one type of species, sodium ions, is left. You can see that, and you can also compare at different temperatures how quickly the standard deviation decreases. So how quickly the sodium metal reacts. And for example, at 700 Kelvin, after only 50,000 approximately femtoseconds, you already have a complete decomposition of sodium. For sulfur atoms, we see that there's an increase in the number of species. We have PS4 groups producing PS4 group, PS3, and so on, together with sulfide ions. And for phosphorus atoms, you can very nicely see an increase as well because of the production of these PS3, PS2, PS1, and so on groups. So by using Matlantis, we're able to get the approximate charge of every single atom over the entire simulation. And this allows us to compare how this system reacts at different temperatures, which I think is, you have to admit, a very impressive feat of the Matlantis software. Now, in batteries, we have, of course, always reactions. It will be inevitable. But one of the ways in which we can get these systems to remain stable is if the decomposition products provide a stability, passivation, that they don't further let the reactions escalate. And so what we did is we took the decomposition products. So we took from the 400 Kelvin output products, we put it in between a new metal slab of sodium and the solid state electrolyte. And we call this the SEI layer. So it's a solid electrolyte interface. It's a layer which contains these decomposition products. And then we ran the simulations again, and you can see that at different temperatures, at the absence of this SEI, that there is quite an energy difference between the different temperatures, showing that at higher temperatures, there was a significant decomposition or reaction between these two materials. But if you have the SEI material in between, well, then you have a very small decrease in energy, which really shows that having this layer here, it really stabilizes the interface. So it shows that it's a good decomposition layer. Now, in reality, the SEI layer is significantly larger in the angstrom, in the nanoscale range, but for simulation purposes, only several angstroms were considered in this study. Now, so far I've shown you Matlantis results, but what's important is that you can also link it to other techniques to validate it. And one of the first techniques that we used is ab initio technique. So we used VASP to analyze this system. And as you can see in this density of states plot, so on the vertical axis, you have once again, the coordinates, so the depth into the model. On top, you have sodium metal. Below, you have the solid state electrolyte. And you can very nicely see that at the Fermi level, Fermi energy level, you have an overlap. So electrons have the same energy at the Fermi level, meaning that these electrons from the solid state electrolyte and sodium metal can interact with each other and therefore react. So thermodynamically confirming that there is a reactivity between both materials. When we look at the partial DOS, so the projected DOS, and you can see that closest to the metal electrons, you have the sulfur atoms. So the sulfur atoms we found were also the first to react. It's the breakdown of these PS bonds. So this once again confirms the results from Matlantis. And you can see also in this figure that we found that there is a band gap for this decomposition layer, for the SEI layer. That also is a good property, which means that electrons cannot easily go into the decomposition layer, which is a good property of a decomposition layer for the solid state electrolyte and sodium metal interface. So the reactivity and the good SEI layer properties were confirmed via ab initio calculations. And we went one step further, and we also performed experiments. We analyzed the decomposition products at the sodium and Na3PS4 interface with XPS. And we confirmed the presence of sulfides and phosphides, which is in agreement with the results from Matlantis. So we confirmed also by doing this experimentally. So to summarize the first case study, we found that the decomposition of this Na3PS4 solid state electrolyte is due to PS bond decomposition upon reaction with sodium metal. And as I will show you in the next case study, this provided a starting point for improving the stability against the sodium metal electrode. We also found that using Matlantis allowed for obtaining results at a significantly lower computational cost, and we were able to validate this computationally with ab initio calculations and experiments. So let me now show you the second case study. And the second case study also showcases another good property of Matlantis, in that you can simulate many different elements on the periodic table. And these results were also published in a paper which was accepted last week. So if you're interested, please, you can have a look at this on this link. So as I explained to you in a few slides ago, we found that this PS bond degradation is central to the decomposition of the solid state electrolyte. So how could you then potentially target a lower reactivity towards sodium metal? Well, one of the ideas that we had was, can you change the chemical properties of these PS bonds? And could you do that, for example, by replacing or doping one of these PS bonds by a PX bond? So you introduce a heteroatom to bond with phosphorus. And the idea is that because of electron withdrawing and giving inductive effects, you're able to change the properties of these PS bonds. For example, if you use an element which has a higher electronegativity than phosphorus, this will withdraw the electrons from phosphorus by means of speech, and as a result will shorten the PS bonds. And we were able to confirm this with electron localization function calculations. And of course, the opposite effect could happen when you have elements such as selenium and tellurium, which are heavier. So we chose these elements based on the fact that they're in the same group of sulfur, or they're either close by and have different properties as radius and valency and so on. So once we confirmed that this hypothesis indeed takes place, we then went on to use Matlantis to simulate these materials. And this really shows another advantage, as I showed you previously, of Matlantis, in that you can simulate many different elements using this neural network potential. So here are the output results. We studied many different new materials. Of course, once again, it's difficult to really see what happens, although we can see that for oxygen, a significant amount of sodium remains. So it would lead us to understand that oxygenated structure has a very good performance. But of course, as I mentioned previously, we only get so much information visually. So once again, we use the strength of Matlantis to get the approximate atom charge, and you can then see it in this figure. Once again, plotted for separate atom types, we can see that for oxygen, and especially take a look at the phosphorus atom charge, you find that very little of the phosphorus has decomposed. It shows the standard deviation hasn't changed a lot compared to all of the other materials, which means that this Na3PS 301 material has a superior performance to the reference system, so to the material that we studied in the previous paper. And here is another way of visualizing it. So you have in blue, we have the sodium metal. So we visualize here the sodium atom charge cross-sectionally. And you can see that for oxygen, the majority of sodium remains, followed by sulfur and then by the other elements. Now we were able to confirm that this is because of chemical properties. For example, oxygen is in the same group as sulfur. It's smaller than sulfur. The valency is also the same. For example, if you look at other elements such as fluorine and chlorine, larger in the case of chlorine, but fluorine it's smaller. However, you have a different valency, so that causes for instabilities in the structure of these PS4 groups. So that's why using oxygen, also from a theoretical point of view, gave the best results. Here's another way of visualizing what happens. So in one of our previous papers, we introduced this RBC technique, which is just another way of looking at how bond length in this case, PS bonds change in function of different elements, in function of different element doping. And you can see that essentially the more color you have, the higher you go in value, the greater the bond length increases when you have, for example, elements which have either a lower electronegativity or elements which are unstable and will spontaneously react. And you can see compared to the reference state, so compared to the Na3PS4 pristine material, in the case of oxygen, there's a decrease in the bond length of these PS bonds. So a shorter PS bond, which means that sodium atoms cannot as easily attack this bond and react, and therefore explaining its higher stability. And once again, it's important to confirm with other methods. And in this case, we also performed ab initio calculations. You can see that as we move from tellurium to selenium to sulfur and then to oxygen, we move further away from the Fermi level. These are the sulfur 3p orbital energy. So you can see that when using oxygen, you have a lower thermodynamic reactivity towards the sodium metal. And when you look at the band gap, you find that it increases towards using oxygen, which is also another beneficial property, which means that less electrons will be likely to enter into the solid state electrolyte. And this is a very good property for solid state electrolytes. And finally, we also confirmed this experimentally using XPS. So you can see when we have sodium and the conventional material, so Na3PS4, we have the presence of these phosphides. But what happens when you have the sodium and the oxygenated structure, you do not have this phosphide peak. So this also confirms once again the superior stability of Na3PS3O1. So to conclude this example, so we performed a screening of a variety of elements in new solid state electrolyte materials. And this is thanks to Matlantis to be able to simulate these many different elements. We also confirmed that these PS bonds are tunable in property by introducing these heteroatoms, and that the oxygenated structure provided a superior performance against the sodium metal electrode. And so in future work, we're interested in investigating the ionic conductivity, as well as further improving the chemical stability, and also including the electric field effects. Now, we didn't study them in these works because we had to focus on the other environmental conditions, but it is very important to also include these effects. And we are aware that we can also use electric field calculations in Matlantis. So that's also something to look forward to in the future. Now, before I end this presentation, I would like to first finally show you another example, in this case, not on ionic systems, but on molecular systems. And this was done in collaboration with ENIOS. So I went for 2 weeks to ENIOS, and I did research on investigating degradation pathways of lubricant additives using Matlantis. Now, ENIOS produces lubricants and lubricant oils, which are used in automotive and industrial applications. And the purpose of these lubricants, and I'm sure that we all use it, even if we're not aware of it, and for example, electric vehicles and so on, is to ensure a low friction and an efficient heat transfer, amongst others, between surfaces. And this lowers costs, increases lifespan of machines, and reduces energy consumption. So optimizing these lubricants is very important for any application. Now, as you can expect, when you have and you have different materials rubbing very quickly over each other, and also exposure to high temperatures and pressure and oxygen, can lead to reactive species being formed. And one of those species are radicals, so single electron containing molecules. And these sequentially break down the lubricant and increase friction and other negative influences, which of course is very detrimental to the performance. And that's why we add additives to counteract this degradation. And one of those types is antioxidants. It's not only in lubricant, but also in, for example, humans. We naturally have antioxidants to prevent such reactive oxygen species from breaking down materials in our own body. And these antioxidants are able to capture free radicals, but the decomposition of these antioxidants can be very complex because of the many different radical species. So if you want to design new antioxidants, you have to really have a good understanding of how this decomposition works. And one such example is of this molecule, BHT. It's a widely known antioxidant molecule. And it could, for example, react with this ROO radical to produce this new species. So in which you literally, the radical takes the proton and you release this BHT radical. Now, if you look at this reaction, it might seem like a very simple, it's not too large, but if you perform it with density functional theory, if you want to look at the activation energy, even with 64 cores, it takes more than a day. And in reality, it took more than a week or up to a month, because you have to find the right transition states, structure, and only then can you have the right energy. Now we performed the same calculation with Matlantis, and with just one GPU, we were able to get it in 6 minutes. So that is a very significant improvement also for these molecular systems. And Matlantis is so fast that we can actually, and that was one of the things that I did during those 2 weeks, is to develop an automatic reaction pathway search script in which you can automatically map the activation energies for these decomposition reactions. And this is also possible thanks to the speed of Matlantis, which allows us to calculate multiple reaction paths, as well as the fact that we can script inside this Matlantis online environment with Python. So we can create our own scripts to use this neural network potential. So finally, I would like to take a short moment to conclude on what we found previously and then my experience with Matlantis. So as also mentioned in the presentation by Rudy, and I can confirm that we found it is very versatile. So as I showed you, we have a very diverse range of elements which were considered in these simulations. We also were able to simulate both molecular and crystalline systems. And I must admit that initially, and some of my colleagues also were a bit skeptical about the fact that can you only use one neural network potential to study a variety of different materials? Because, for example, in molecular dynamics, if you're looking at a protein system, you have specific force fields for those systems. And if you're looking at a metal system and so on. But in this case, what Matlantis has, it has optimized and dedicated neural network potentials for molecular systems and for crystalline systems. There's many different types. So it can use the right optimized neural network potential for your system. Also, performance, we have it much significantly faster than ab initio methods, yet at the same level of theory. So you can also simulate the reactions. And it's also very convenient in that it's an online simulation environment. So you can access it from your computer. There's no need to have a local installation or a supercomputer installation. So you can just access it from anywhere using your browser. There's also very extensive documentation with many example codes. And the customer help is also very responsive, and especially they're very happy to hear about new features that they could introduce into their software. So with that, I would like to thank everyone at PFCC for allowing me to give this presentation, and also at Free University of Brussels and Nagoya Institute of Technology, as well as at INEOS. And I would like to thank you for listening, and I'm happy to answer any questions, but I will leave that to Rudy now. Thank you very much.
Thank you, Lieven. That's very very impressive research. I mean, let's keep in mind this is done in the framework of the PhD. I think what you presented today is quite impressive, and not just because it's Matlantis, also the methodologies that are chosen and the work you have done. So we have indeed received some questions. What I will do, we have a couple of questions on Matlantis himself. So before going to Lieven's topic, we will try to answer those from the PFCC side. So let us see what we had. So the first question was, which optimization method does Matlantis use? Is it quantum mechanics based, or is it molecular mechanics based? So we have today, actually, besides myself, also other colleagues who are from PFCC, some of them being part of the technical support team and experts. So I would like to let them actually answer this question. Taku, if you want to do that, please.
Hello, my name is Taku Watanabe. I'm a lead researcher at PFCC. So let me answer this first question. So the optimizer, actually quite many of them are available through the typical molecular simulation type optimizers included in ASC and LAMPS. So those include local optimizers like very similar to type of BFGS optimizers, as well as number of more minor optimizers included in these two libraries. I think there are also some global optimizers for finding global minimum configurations. As for the type of method this technique is based, it is, well, you can imagine something very similar to molecular mechanics, but it works in a very similar way to DFT calculation. So it's not clearly it's based on QM or MM, but you can, the technology that seems very similar to this technology is probably something like a reactive force field. So our model is trained using DFT calculations. So I think this is a kind of accuracy that you can expect. I hope that answers this first question.
Yes, I think, thank you very much, Taco, for this answer. And if anything is unclear, don't hesitate to contact us. We'll be very happy to get back to you, of course. We had another question on Matlantis itself again. The speed gains are obvious. How good is the prediction accuracy when you go outside of the trained data set? Risk of extrapolation issues. I think what Lieven was presenting today is already part of the answer. You could see that with one case study. We have other case studies that we could show. I would prefer today to finish answering your questions, but we have several case studies that you will find on our website, including catalysts and screening of thousands of configurations in a very short time that would have actually used up months or years to do by DFT. So the answer is yes, we have tried a lot of different systems, and usually the accuracy is really good and it compares very well with DFT. So that's the answer I wanted to give here. But again, we are happy to share the case studies that we have. So please come back to us, and we will answer this. The next question is more related to what Lieven was presenting. Sorry. So, is there a possibility for a sodium to get precipitated rather than intercalating in the Na3PS4 beyond certain solubility limits? So, Lieven, I don't know if you want to, if you can answer this.
Yeah, I first of all, the system is completely solid state, so I'm not sure. I mean, probably you mean instead of precipitate, you mean like, for example, dendrite formation. In the case of dendrite formation, that also happens in solid state systems, but it's limited. But indeed, if you really want to study like those effects, then it's interesting to increase the size of the system. And I think with Matlantis, we're able to do that. So that will indeed also be an interesting study, for example, on how to see how this sodium metal could form dendrites at the interface region. Thank you for your question.
Yeah. Thank you for the answer. For the same person, another question. Also, the lattice constant for the final output is going to change significantly from the input structure. Mm-hmm. How would that effect be incorporated?
Yeah, I think in any case, there are these changes happening, but how this will influence, I'm not completely sure yet. I think we have to study that in further detail. But once again, looking at these, these simulations provided so much output information. So analyzing all of that, all of these different aspects is very interesting. So we'll take that into account also in future studies. Thank you.
Okay. Then another question for you. For case study number 1, you're presenting very good acceleration of the studies of batteries interface with the neural network potential MD, which opened the doors for understanding which opening a closed door so far, so things that were not possible before. What are the results of the simulations benchmarked against experimental results?
Yeah, so yeah, as I showed during the presentation, we did it using XPS. So I think that really is a very strong validation for this technique. So I hope that answered your question.
Yeah, I think indeed you presented, you already presented that during the presentation. The next question, use case 1 shows a nice story where everything lines up very nicely. Did you also run into calculations where VASP and Matlantis did not agree?
In our case, I don't think we saw those effects, but the only change was, for example, when you have the user input structure, like the one that you draw in your design programs. The initial optimization was slightly different in VASP, but the end structure converged. But that's probably why you can see that there is a slight deviation at higher energies. That's because the input structure was just slightly different. but in the end, both converge to the same energy. So this didn't provide any problem for us.
Okay, I see. Let's continue. We're almost up to it's almost 5 o'clock here, but I think we have a few more questions. So I think this should be finished quite soon. Next question. In your opinion, what is the most time-consuming step while using Matlantis platform?
Most time-consuming step. Honestly, the simulations, as soon as you submit them, of course, you cannot submit many simulations. You can't submit 10 simulations at a time because you also have to take into account the system itself. But simulations that you run, they start immediately. And in terms of the most time-consuming step, I think that's the calculation time for what would be a single SCF calculation is extremely fast. So. But I know that the researchers at PFCC and PFN are working on increasing the calculation speed. So for so far, I don't have any real problems with the speed of Matlantis at all. Thank you.
Right. Okay. Then let me see. I'm trying to see. There are questions that are for you more specifically. See. There's one question maybe that we can answer as PFCC. Could you use this software to study the effect of catalyst on activation energy? Yes, indeed we can, and this is actually what a lot of our customers are doing. I mean, one of the important customers and partners is Ineos. You can imagine as an oil company, catalysis is one of the key topics. And actually, this is the way I would say one of the application fields where Matlantis was started. I mean, the whole story dates back to at the time where PFCC did not exist yet, and it was still PFN and Ineos. And catalysis was at that time one of the most important topics. And we have some very nice case studies on that as well, where, for example, for syn fuel synthesis, you have a cobalt surface, and you study different metal promoters for this catalyst. And because Matlantis is so fast, you can actually screen thousands of configurations with different promoters. Then you can calculate your activation energy using a very well-known NEB, so the nudge elastic band. And then you find which method gives you the smallest or let's say the highest reduction in terms of activation energy. And that would be your best candidate. And that was done. Vanadium, for example, was the best candidate in that case. And experimentally, this was also confirmed. So that's one example where we have catalysis that is being studied. Maybe a question for, I'm going to extend a bit beyond the time. I understand some of you might have to jump into another meeting, so that's okay. If you have a few more minutes to stay, we'll be happy to answer the rest of the questions. Maybe a question more for PFCC as well. To our tech team, can you elaborate a little bit more on the long-range electrostatics in the Matlantis ML potential? And what kind of short-range descriptor is underlying the Matlantis potential? Maybe Taku, since you are answering the first question, is it something that you can take as well?
Okay, thank you, Rudy. So about long-range interaction, electrostatic interaction is actually the kind of interaction that's not very well described using our neural network potential. Our neural network potential right now is limited to modeling, using a model with a specific interaction cutoff, which is around 6 angstrom for the direct interaction. But this is a convoluted neural network. So if you have multiple atoms in between this 6 angstrom, you have interaction actually propagate, typically on the order of 20 angstrom. So, but still there is a significant, I think, uncertainty in the electrostatic part of the calculation. So that's the part we need to make improvement. So the short-range interaction, there is another factor we need to consider is this van der Waals interaction, which is typically a very weak interaction and not very easy to capture accurately using even DFT. And there are several well-known method exists to do this type of calculations, but we use Grimm's van der Waals collection, the D3 collection. So that's the kind of interaction model we can use at this moment, but we are continuing to make improvements on our model, so hopefully we can improve the accuracy in near future. Thank you.
Yeah, thank you, Taku. There will be probably a bit more questions also for you coming. But let's see. I will take them as they came, because otherwise. So another one related to Matlantis. Say that you find a case in which the prediction is wrong. Can you retrain on data unseen and improve the network?
So as a part of the service of our product, we have cross communication with our customers, and if we get reports from our customer that for certain applications accuracy is not good enough, then we will bring this back to our development team and discuss whether we can make any improvements for this specific type of systems. But generally speaking, we don't really try to tailor our model for improving specific applications, just because we want to maintain overall consistency of our model, and we want to improve the accuracy of the model, but at the same time, we need to make sure everything is consistent while we are making these changes. So the feedback from our customer is very much valued, and we want to try to include that in our improvement process. But we cannot guarantee when it's going to happen, and we have to basically consider our roadmap and how it aligns with our development plan.
Right. Indeed, the versatility of the system is one of the real strengths, and that's something we want to keep, of course. But we, I mean, it keeps improving. I mean, Matlantis is not, we don't have an NNP, so our neural network potential is not defined and carved in stone. That's something that we keep improving. Also, calculation methodologies and speeds, they keep being improved. So we have scientists, researchers working on this. So this is an ongoing improvement. There is one question for you, Lieven, on the last example that you've shown. So the work that you have done as part of your internship with the short stay you had with ENEOS. In the last example, how was the reaction path evaluated? If you can say, of course, and what kind of algorithm is used?
So unfortunately, I'm not allowed to say which method was used, because currently it's a proprietary method, which patent has been taken on. But we do have a big advantage over traditional NEB, that it's an automated search, which allows you to find the transition state much faster than conventional NEB methods.
All right, thank you. Yeah, that's one of the big strengths of Matlantis. I mean, the fact that you can program everything in Python, I mean, possibilities are almost unlimited. I mean, you can combine with the speed and the versatility of the, let's say, of the engine. There are a lot of things that can be done. And we are just now scratching the surface. We are just starting to actually apply this. You can simulate easily thousands of atoms. We're also trying to improve it to simulate even larger systems. Polymer systems, for example, are on the radar for us. So we are trying to, at some point, be able also to treat those. Biotopics as well, such as modeling enzymes. This is a challenge that is also being looked at today in our companies. So yeah, please stay tuned, because a lot of new things will be coming up.
And if I could just, sorry, if I could just also say that the method for finding the reaction pathway is indeed, I think, if I'm correctly understood it will be available in Matlantis once the patent has been applied for.
Right. Yeah. Okay. Thanks, Lieven. Let's see. We have 2 or 3 more questions. We will take those, and I think then we can then close our webinar. They are related more to Matlantis itself. The first question is the pre-trained model atomic interaction potential freely available? data from DFT calculations, right? Acceleration due to graphic neural networks you are showing could question the future need of HPC. Okay, so I can take this one. So the pre-trained model atomic interaction potential, no, it is not fully available indeed. You could see this is based on a huge number of DFT calculations that actually will run on Preferred Network's own supercomputer, which is one of the largest supercomputers. Actually, it was ranked in the Grid 500 list. And this is really the core of the technology. So this is not something we are going to make freely available, but of course, we are very open to collaborations and also to work with academics. We are still new. We are a very young company. We want to make ourselves known, and so we try to leverage also collaborations as well in the academic world. So if you are interested, or even to tell us about what you would like to see improved, or if you have something that you know how to improve, you can always contact us, and we'd be very happy to discuss. And then your comment at the end is acceleration due to this could actually question the future need of HPC. Yes, you're right. We have actually a lot of customers telling us it's very nice to have a cloud service, but we would like to use on-premise because we have our own computers. We understand that, especially from customers who just bought their own HPC. I mean, they want to use it, of course. But at the same time, as you just mentioned, I mean, the speed of Matlantis and the easiness of using it. I mean, we can update, we can fix issues since it's online. There is no need from the customer side to actually reinstall things or to worry about which version they are using. That is indeed one of the big reasons why we actually now still focusing on cloud service. We might consider on-premise in the future, but today that's a question we're asking ourselves. But for the time being, it's only cloud service. And we think customers who were hesitant first, when they took the step and actually started using Matlantis, I think now they are very happy that they are actually using Matlantis and not an HPC. I think you could see that also the slide I had from Toyota, where you compare the speed of Matlantis to even the very fast Japanese supercomputer. I think the question is easily answered. Then we have two more questions. Thank you for the nice presentation. Very interesting platform and interesting science. Question from Matlantis regarding the excellently reported accuracy. So two questions here. Number one, do you incorporate any uncertainty quantification? And question two, I only find energy-related errors. Do you also test for force-related errors? Are they equally good in the various case studies? Taku, I might use you as well again here, if you want to comment on this and try to answer.
Thank you. So I know some of the softwares, like for example, BAS, on the fly, they can compute, generate some models, including uncertainties, but our model operates quite differently, and we don't show the direct comparison of our training data uncertainty with our model, but we should publish some papers that include actually out of domain data uncertainties included in references. So if you can check our Nature Communication papers, I think there are several uncertainty values reported for both energy and forces. And regarding the second question, it's a bit difficult to make this comparison just because it's hard to say which one is better, just because the units are different, totally different on these two values. In generally speaking, I think I should say energy accuracies are probably better in that sense, but I think both energy and forces are generally good enough to perform this kind of simulations.
Right. Thank you, Taku. And then that would be our last question. That I will answer myself. I think it's okay. I mean, although this is also already to you, Taku, but are there plans to include Monte Carlo capabilities in the future? So yes, they are. Actually, we already have a tool, a Monte Carlo tool that is being tested internally today. And of course, once this is ready, to be made available, we will make it available to our customers. So there will be a Grand Canonical Monte Carlo. You can imagine applications can be very interesting, combined to the high speed of Matlantis. We already have customers actually testing these kind of features. For example, when you look at the metal organic frameworks, and if you want to start looking at separation of gas or adsorption in these frameworks, and if you want to start very large, building very large databases, you can actually combine Matlantis with Grand Canonical Monte Carlo, and this becomes even more powerful. And so, yes, this is something we are working on, and this will be included in the near future. All right, so this was the last question. So we finished a bit later than expected, 15 minutes to be exact, but I think it was worth taking the time. To those who are not with us anymore online, we will have the recording anyway. It's sent and shared to you. So you'll be able to see those questions. Before closing, I wanted to thank everyone for their participation. Of course, I want to thank Lieven for giving such a good presentation and the very impressive results that he managed to generate during the time that he spent in Nagoya Institute, the Institute. I mean, he has not spent his whole PhD there, and I think he has already generated very interesting results. He has proven that he managed to build also methodologies, and I think, and that's why we wanted to have him present this today. And it also shows that the interest and the level of research you can achieve is not related to how old you are. So thank you again, Lieven, for that. Thank you all the colleagues from PFCC as well for answering those questions today. Those online like Taco that you can see now, but also the ones behind the screen that you didn't see. And yes, please stay tuned. We hope to see you again during our next webinars. I invite you to visit again, if you have done so, our Matlantis website. Feel free to contact us to request a online meeting. We'll be very happy to organize one and to look at more specific topics that you are interested in. So thank you again for today, and we wish you a very good day for those in Europe, and a very good evening for those joining from Asia. Thank you, everyone, and see you soon.
Very well done.